Yeah, good evening. So revision session, sir, we are going to have that separately as well before the quiz, right? Is that correct?
Yes,
Yes,
sir.
yes.
Okay, okay. Yeah, then we'll have that separately. But for now, I was just willing to take some portions from symbolic execution again, because that was left out from the previous session. And so I just want to go over that also. Before that, if you have any questions, you can ask. Otherwise, I'll share my screen and uh, you know, we'll start with that.
So you should go ahead.
Okay, thank you so much. All right, please let me know if the screen is visible.
Yes, sir, visual.
Okay, thank you. So this is symbolic testing again. We have covered it in the previous session also, but due to some technical issues, some portion of the session was not having audio. So the like what I was saying was not audible. So I plan to do it once again. Like we'll do a recap of whatever we have discussed in the previous session also, and hopefully that portion which was missed in the recording will also be covered again. So let's start. So this is regarding symbolic testing, and I wish this session to be slightly more interactive. So that will be better because otherwise, it so happens that if I don't get any response, I assume that things are clear, and therefore, if there are some issues with the audio also, we are not able to, catch it because nobody responds. So we just assume that everything is clear and move forward. So that also sometimes becomes an issue. So please do respond whenever I just ask, just so that uh, I am, I understand that at least the audio is correct and you're also understanding what I'm trying to mention. Okay, let's start. So again, I'll just go over that briefly because these portions, I think the beginning, few slides from the beginning has already been covered in the previous session. So you might as well, go uh, at least for that part of the recording, you can watch it from YouTube and it'll be clear. But for the rest of it, we are anyway going to go through that. So in any case, I'll just revisit certain portions from here as well. So again, symbolic execution is a means of analyzing a given program to determine what inputs cause each part of the program to execute. Right. So as we've discussed in the previous class also, you have conditions, right? Recall from CFG also, you have this control flow graph corresponding to a source code. So what happens is that you have conditions due to which you will follow certain branches or not follow for that matter. For example, if you have a if condition, then if that becomes true, then you go inside that branch. If it becomes false, then you follow the other branch. So it is like the else case, right? Even if the else case is not there, you might as well continue executing. So sorry, continue executing the program and go somewhere else, but you don't go into that particular branch. So what we do in symbolic execution is that we have conditions and then we try to analyze those conditions and see what inputs I mean, like what conditions, basically what kind of input if you give, what conditions are being satisfied, and therefore what is the path that the program is following under those inputs. So that is what symbolic execution is about. Is this clear? Is the definition clear to you?
Yeah, yes.
Okay, sure, thank you. Okay, now so the point to note is that uh, since you are having different branches in the a control flow of the program, right? So then if you want to test the different various different execution paths the program might take under certain inputs. So it suffices to check for those conditions, right? For example, if you have two branches and you want to go in each of them, like for example, if you do it in, let's say for example, edge coverage, right? So you have, let's say, a branching occurring at some point in the node in the control flow graph. Then you want to go follow both of these edges, right? So what do you do? Is, for example, if you have a condition there, you make it true once. So you go inside that and you make it false in the other case, so you don't go inside that, right? Therefore we'll cover both the cases. So something similar is happening here as well. Okay, all right. So now there is this notion of reachability and infection also. Reachability is concerned with the fact that whatever portion of your source code you wish to test, you have to reach that, no? So for example, if you want to check something which is under, let's say, a loop, or for that matter, under an if condition, then you must satisfy that to be able to reach that part. And then you'll be able to test that, right? So it makes sense. You want to check some part of the source code, you have to reach there first, and then only you'll be able to test that. So that's one. The other thing is infection. I'm so sorry. Yeah. So the other thing is infection. What happens in infection is that uh, you have a state in the program. So we'll talk about these things as we move forward also. I don't want to go into much detail because of two reasons. One is that there's a lot to cover in this slide itself, and most of whatever I'm covering right now has already been covered in the previous session, so people might as well go there and watch the recording. Okay, so what happens in infection, you have this state of which I have discussed in the previous class also. So if the state of your program, let's say you give some input, okay, then at a particular point, at a particular line of code, if your state was something, let's say we call it A, right? So you have a state A under a certain input, then you give another input, and your state of the program at that very place is different. Let's say state B, right? In that case, we say that infection has taken place, which is to say that due to the input that you have provided, the state of the program has changed, as in the path, the execution path that this program was following is not the same as that of it was following for the other input. So basically, you are able to infect in some sense, you know, the behavior of the program. So that is what we say, and these things we are going to learn more about these reachability and infection and propagation also in the mutation testing topic that is coming up later in the later week. Okay, so that is what. All right. So sorry. Yeah, these are some references that are from the software testing literature regarding symbolic execution. So symbolic execution is one way or one paradigm with which we do testing, for certain things in the program. However, software testing in itself is it's a vast field, and there are so many other techniques also, of which symbolic execution and its variants are one. Okay, so we are going to discuss some of them. Okay, so it is best understood through an example. So we'll just go briefly over the example and things might be clear. Okay, so here we have a program of which there are 6 lines here, you can see. Okay, this is a sum function. So we're just assuming the entire signature is not given. We're just assuming it to be a pseudo code here, but we can make out what exactly it's trying to do. So we have 3 arguments that we're taking in as the input. So these in some sense are your inputs, right? If you talk about this function only, then A, B, C are your inputs. Okay. I hope I'm still audible. Can somebody please confirm?
Yeah, yes.
Okay, thank you so much. So I just wanted to do a quick check. So I'll be doing that, every once in a while just to make sure that the audio is going through properly. Okay, thank you so much. So we have 3 inputs, A, B, C. Okay, you're taking it in, and basically we are summing up. So what is happening is there are three other variables that are there: X, Y, and Z. Okay, so we are adding to X we have A plus B. In Y we have B plus C. Whatever output comes in, we put it in Y, and Z similarly we have, so sorry, X plus Y minus B. Okay, so that goes to Z, and then finally we are returning Z. Okay, the value for whatever z holds at line number 5, we are going to return that out of the function. So this, in some sense, is the output, right, of this particular function that you're going to get, right, for some certain input that you provide for a, b, c. Okay. Now, uh, please pay some attention to this table, what this table is trying to say. This is what the state basically is. It's one way to represent the state. There are several ways to represent the state, but tabular format is some, some format in which we can represent the state. So, uh, okay, so the state basically says that at every instance when the program is running, okay, note that we're talking about the, when the program is running, okay, we're not talking about the code, okay. So when the program is actually running on a machine, then at every statement you got some state of your program, right? So for instance, if you talk about statement one, here statement refer to the line of code that is being executed by the computer at that moment. So for example, if you talk about line number one, then this is that line. Okay, please try to relate these two. So please pay attention to this row. What it says that when statement one is executed, at that moment these are my variables and these are the values that the variables are holding. So for example, x, we don't know what x is holding, so that's a question mark because we just started here, no? So x is not initialized till now. X, y, z are not there because we are at line number one right now, but we know that in the state there are these variables are involved here. So x, y, z and a, b, c are the variables that are involved in this function. So we have written all of them, but then in line number one we don't know what the value is for x and y and z. However, for a, b, c we know what are the values because that is the input. So we are giving that, right? Sorry. So we are giving that 1 comma 3 comma 5 is a, b and c that we are giving inside of this. Okay, so then what happens is that after line number 2 is executed, note that x is initialized here. So x is a plus b and therefore we are getting 4 because you see that a was 1, b was 3, so we add the 2, we get 4 here as the value for x after statement 2, of course, right? And wherever you see a dash, that represents unchanged value as mentioned here. Okay, so these are the things which are not changed. So we are just putting a dash there. Okay, now similarly for x, sorry, for y also we have 8, right? Because y is b plus c, which is this 3 plus 5, which, sorry, which gives us 8. And for z we have 9, which is x plus y minus b, so uh, that is 12 minus 3, right? Because this is 4, this is 8, 8 plus 4 is 12, x plus y, and minus b is minus 3, so that gives us 9. And finally, we are returning 9 as the output because we are returning the value of z. Okay, line number 5, note that. Okay. So that is what this table says. Okay, so this is like a state map. Okay, we are mapping the state of the program after each individual line of code is executed. And finally, the output also is there. Okay, so I hope this table is clear. Is this table clear? Are there any questions at this point?
Sorry, yeah, here
Hmm.
the question mark represents the undefined or uninitialized.
Right, right. This one, correct.
But yeah, but in line number one, there is no even not declared. X, Y, Z, Z are not declared.
Hmm. Right, your point is valid. I understand your concern. So the thing is, we know from source code, right, that these are the variables that are involved. That they are going to come, in the state at some point. I totally understand that at line number one we don't have x, y, z. So how do we know? But then we know that x, y, z are going to come into the state because these are all the variables that are involved. So basically, when we are trying to map out, we'll write every variable that is involved in the function. However, some may be initialized, some may not be initialized depending on the program that is there and depending on where are you in the program. So for example, if you are at statement number 3, then in that case, x, y, z are holding certain values, but at statement 1, we don't know what they are. So,
So
right,
even it is not declared at line number one. No?
right, because we are seeing the source code, right? So we know that these
Yeah.
things are coming in, right?
Okay.
Then, okay, if you want to So if you want to put it that way, because okay, there's another thing about this. So it's good that you've asked this. So the thing is that in the actual state map, the thing that I'm calling the state map, no, you won't have that mapping yet. So it's like a dictionary, right? The state map try to relate it with the dictionary. So what happens in a dictionary, no? As and when the values come in, we put it there. So for example, if we talk about statement one, here we are having a table, right? Therefore, we're writing it in all the columns, right? For example, all the variables that are there in all the columns. So we have X, Y, Z, A, B, C. That is the complete set of variables that are involved in this particular function. However, in the actual state map, as we'll see moving forward, as and when you encounter a variable, right, then only you will kind of add it to the state map. So you are correct in saying that when we are at line number one, there is no x, y, z, and so there are no variable assigned to that. But then because this is a table, we have mentioned that in the state map, in the actual state map, it will only come in when you actually have that variable assigned to something. So for example, x will come in only at line number 2 onwards. Okay, hope that clears your doubt.
Yes.
Okay, sure. Okay, so now slight distinction here actually, and this is the very important thing to actually notice between the normal execution that happens, with regards to certain inputs that we give. So before we move forward, let me just take you to uh, test cases. Okay, so what happens in test cases is that we have inputs, as we all know, we provide the inputs, and along with that we have expected outputs. Okay, so we provide the input, so we know that okay, if these inputs come in into the program, then the output should be this. Okay, then if the expected output is actually matching with whatever you get out, as the output of the program, then you say that the test case is passed. Okay, which means to say that whatever you expected, you've got that, then it means your test case has passed. Okay, I'm so sorry. Then it means that test case is passed. If it is not matching, let's say I provide this 135 and I expect 9 to come out. Let's say for some reason I get a 5 out of this, right? Then I'll say that my expected output is not matching in that case, right? So the test case will fail. So this is the normal execution, right? The thing that we already studied in the previous weeks also. That is what we do. We give inputs, we try to see what the actual outputs are and what the expected outputs are, and we try to match in the two. Okay, so that is what happens. Now contrast this with symbolic execution. What happens? You have everything is the same as previously, but now you're not providing any concrete value to those variables, which is to say that instead of providing certain values, like in this case we provided 1, 3, and 5, here we are only saying that a is going to be alpha 1, b is going to be alpha 2, and c is going to be alpha 3. So these are the things that are called symbol. We're just having a symbolic representation of the value that that particular variable is going to hold. So for example, instead of providing a with something as the input, okay, note that these are inputs only. So whatever inputs may come into the function, we are assigning symbolic names or variables to those particular variables of the function of the input. So for example, a we assign a1 there, b we have a2, c we have a3. Okay, so that is one of the most important differences that one needs to understand, that instead of providing concrete values, we are just providing symbolic values to those variables. Okay. Now there is this thing known as path constraint or path condition, as mentioned here also. Okay. So we'll talk about this in detail moving forward. But this basically says that what are those conditions. Notice that I mentioned about the conditions being satisfied and the program following a branch or not following the branch. So try to relate it with that. So what happens is that to to follow certain parts in the execution flow of the program, you have certain constraints or conditions, right? You may have a if condition somewhere in your code, right? In that case, if that becomes true, you go inside that branch, otherwise you won't go inside that. So that is what the path constraint is supposed to hold. Okay, now in the very first case, notice that when we are just starting, we have to start, no? If we make the path condition false, then we cannot move forward. Since we have to start somewhere, initially the path condition is always going to be true, because you have to follow this path. You have to start with this path. in the execution path. Therefore, we always start with path condition being true. Now, if you have certain conditions in between, which is not the case in this particular function, there is no condition, no if condition, no loops, nothing like that. So in that case, it is always going to be true, right? It is never going to become false. But as you'll see moving forward, that in certain cases, if the path condition becomes false, then you're not going to follow that branch and vice versa. Okay, so that's what happens. Is this clear? Is this clear?
Yeah, if there will be, if loop, if statement, then it might be false
Yeah,
and
it
true.
might, depending on whatever the condition is specified inside of that if condition, right? It depends. So we'll see example of that moving forward. So now notice that instead of providing sum of 1 comma 3 comma 5, as was the case previously in the call, we're saying a of a sum of alpha 1, alpha 2, and alpha 3. So these are my inputs, and these correspond exactly to whatever arguments were passed, or the arguments, or parameters which were there in the function signature. So you have a there. The first one is a, the second one is b, the third one is c. So we'll just map those to those. So for example, we have a that gets a1, b that gets a2, and c that gets a3. I mean, like, we're calling it alpha basically. This is alpha, not a. So alpha 1, alpha 2, alpha 3. Okay, so this is that. Okay, now comes if condition. So that will make it more clear what exactly is happening with these path constraints and how do we do that, and what is exactly the point in doing it like this instead of providing concrete inputs. Okay, notice one more thing. So when we say symbolic input, we mean that we are just providing a symbolic name to whatever variable we have and executing the program on that. However, when we say concrete input, which is to say that we are actually providing some value. So these are concrete values for ABC. Here, these are symbolic values for ABC. So that is the difference. Okay.
Sir, here,
Now,
is there any error in this slide? Like,
uh, mhm,
if we add x plus y minus b, x
mhm.
plus y minus b, it will alpha 1 plus alpha 2. Yeah, yeah, right.
Yeah, that comes out to be the sum only. That's the point, right?
Uh,
Because
Sorry.
I understand, because there is this minus also, no? So that gets cancelled out basically.
Yes, okay.
Right, right. That's what happens. Okay. Because one of the b's get cancelled out, no? When you sum it, you get two b, one b gets cancelled out. So that's what. Okay, so you get the sum at the end, but that's okay. So we are just providing the values, and what we're doing essentially is providing the values and running on those values, and then we are getting formulas basically, whatever, whatever is the uh, symbolic representation of whatever the function is going to do. Okay, all right. Now, just quickly go through this program. What happens? So we have a twice function to start with. Okay, and just give me one moment. Yeah. So yeah, we have a twice function. What happens is that we're getting an value, integer value, in the twice function. Okay, that is just going to return the twice of whatever you provide. So if it is 10, let's say, then you're going to get 20 out of this particular function. That is one function. Okay. Now there is this another function. There is a small typo here actually. We should have the brackets also in the test me function, because that's essentially a function again, but we're not having that. But that's okay. We'll just take it as a function only. The same thing. So we have two arguments or parameters that we're accepting in this particular function. That is int of x and int x and int y. That is integer x and integer y. And this is the thing that is happening. So we're actually having to. I mean, like, we're going to test this function only. So we'll talk in terms of this function only. The other functions are uh, depend. I mean, like, this function is dependent on the other functions that are there. For example, the twice function is being used here, which is defined here. So that's what this function main is, the actual function which gets executed first. This is like the entry point. Okay, the very first function that is going to get executed when the program is run is going to be the main function. Okay, so here what we are doing for x and y, note that there are two inputs only for the test me function, because we are going to test this function only. There are two inputs, x and y, as you see. Okay, so when the program runs, we go into the main function, we take x. For x we take a symbolic input, some symbolic input, because note that we're not providing concrete values. So it's just a convention. We just say that, okay, some symbolic input comes into x. It's like assigning some value. So for example, we say x is alpha 1, right? Some mapping that happens. Okay, similarly for y also, and then we run that particular function, whatever we want to test, on those symbolic variables. So xy, we provide it to test me, which is actually a symbolic variables, and then we'll move forward with this. So we'll see what happens here. So what happens here is that basically whatever input you provide, you're going to run through the program, and you will write the expressions that come out in the terms of the original input variables that are there. So for example, here we have z, right? Notice this. Z is equal to twice of y. So what we are going to write write for z is z is going to be equal to twice of whatever the symbolic value for y is. So let's say it is y naught, then z is equal to twice of y naught. That is how we get the expressions. Okay. So when we are calling this function, actually what we are getting in return is twice of whatever was provided. So if I provide y naught here as the value for v, then we are getting twice of y naught, and z is equal to twice of y naught is the expression that I am going to get at line number 5. So the value for z is going to be equal to twice of, let's say, y naught. I'm calling y naught for the symbolic name that is given to the y variable here. Okay, so that is what happens here actually. See, I mean, this is the concrete state. Here, these are just arbitrary values. We've just given it for an example, just to contrast how it happens. In the two cases. In the symbolic case, we have x as x naught and y as y naught, as we know. Now z becomes twice of y naught, because that is what happens. You have y which goes inside the twice function. It comes out as twice of y naught. So that is what you get the value. Uh, that is what you get as the value for the variable z. Okay. At which line? At line number 5. Okay, so hope this is clear, and this, I think, is the answer to your question, which you asked previously also, that when we don't have the variable, how are we writing that in the table. So in this case, what happens is that as and when you encounter any variable, you will map it in the symbolic state that we have. Okay, so if you're going to get a new variable somewhere down the line in the program, you will add that to here in the symbolic state. I'll talk about PC, but before that, are these things clear?
Yeah, yes.
Okay, okay, thank you. So now path condition is, so just after line number 5, what happens is that we have a if condition. Okay, now that is going to make things interesting. So see what happens. We are saying that if z is equal to x, which is to say that if the value for z is equal to x, then we are going to go inside this branch. Okay, what is this branch? This portion of the code, line number 7 and 8, is only going to execute when this condition is satisfied. As usual, we are all familiar with if loops and how they work, right? So that is what happens. So that is the path constraint for the first if condition. Okay, we are not writing the line numbers here, so please don't get confused. Actually, we are just writing out all the path constraints that we are getting. So here we have at line number 6 the path constraints, because uh, try to see it this way: z is actually twice of y naught. So we're just replacing everything in terms of the original variables that are x and y. Okay, so what is z? Z is twice of y naught. That is equal to, this is the predicate. Okay, the predicate is twice of y naught is equal to x. So x is what? X is x naught, no, in the symbolic input. So that is what we have here. Twice of y naught is equal to x naught is the first path constraint if we want to go inside of this particular if condition. Is that clear? This portion?
Yes, sir. And
Okay. Now the next one here. Okay, I think there's a typo here, small typo. So actually, what happens is that this should be greater than, because to get inside, if you're talking about going inside of this inner if also, which is at line number 7, then you have to have x greater than y plus 10, right? Here it is written as x not less than is equal to y not plus 10, which is wrong. It should actually be this one. And again, there is a typo here. Should be x naught basically. So x, I think some mistyping occurred, because of which it is written as x plus 0, but actually it is x naught greater than y naught plus 10. So this is, I think, some issue. We'll just report it and get it fixed, but this should be x naught greater than y naught plus 10, because that is what the condition says. Okay, so you have that condition. So sorry. then you are going to reach this particular line of code which is having the error. So we are assuming that there is some error in a particular line in your code, and then we are trying to see how do we reach that. Okay, now try to relate it with the reachability definition that we gave. Okay, so we have some error. If you want to test that, test that portion of the code. Let's say my error lies somewhere here, somewhere inside this branch. Okay, only after this condition becomes true. No, there might be other code here inside of this particular branch, right? So I want to test something inside that. So the very first thing that I must satisfy if I want to test something inside that is the condition, right? Otherwise I won't even go inside, and I won't be able to realize that there is an error. Okay, so that is what reachability is concerned with. How do you reach a particular portion of the code that you want to test? Otherwise, so let's say if none of my test cases, it so happens that this condition is satisfied, just for an example, then in that case I won't be able to ever see that there lies an error inside this part of the code, because I'm not going to go inside ever, right? So that is why it is very important to check for all these conditions. Okay, so all right, so again, so we are assuming that we have to reach somehow this statement, line number 8. Okay, so now notice that as we are executing the program in a symbolic fashion, which is to say that we are doing symbolic execution on this particular program that is given, then as and when the program moves forward in its execution, we are getting constraint. No, so what we are doing is basically we are collecting those constraints together. So this is the first constraint that we encountered, the second constraint inside of that, right? So and then we reach there. So in the predicate terms, uh, you know you will get something like this. This is the actual path constraint. Now how do we follow that path? So for example, if I want to reach this path, these are the constraints that I must satisfy. Now notice one more thing, that if we have this if condition inside of which there is another if condition, so then that needs to be an and, right? Both of these must satisfy, therefore you can go inside, right? So this needs to be an and, right? Should not be an or. So if this and that. Okay, so therefore we are anding those two conditions. Basically there's this and symbol in between these two conditions, right? So we say that this is the first condition and the second condition, and therefore we will reach the error. So this uh, is the path constraint that we get, okay, as a result of doing symbolic execution on the given program. Is this clear?
Yes, sir. Will there be any case where or predicate will be used?
Yes, of course there can of there can be, like for example, if I'm sorry, I'm getting an echo, could you please mute?
Yeah.
Yeah, yeah. So your question is, can there be an or condition also? That is a perfectly valid question. So of course there can be, because depending on the if condition, here it so happens that there is an and condition, but it might be the case that your condition is such that, let's say we say here itself in this very if condition, we say that z is equal to x, or this condition, right? Let me like we can combine the two, and then we can have one large condition that says this or that. Right. Here and is happening because of the nesting, because we are nesting the two, right? So we can also write it something like this, right? Z is equal to x, and we do two times and, right? In the pseudo code also. So and this condition. However, we can also do or there, right? So this condition or that condition. In that case, you can sorry, you can get an or also. Here we have an and. Okay, because of nesting. So that is what. I hope it is clear. Is this clear?
Yeah, yes, yes.
Thank you. Thanks so much. Okay. Now, so I talked about symbolic execution, that I hope is clear. So as the program is running, right, you're trying to, in some sense, get every possible branch that we can have depending on the condition that we are right now. For example, we are at right now. So for example, we have this very first condition that is there, the outer if in the example program, right? So there are two outcomes out of this. Either this is false or this is true, right? Similarly, for the other predicate, note that when this is false, right, we are not having any other condition, because we don't have any other condition, right? So this particularly maps all the conditions that are there. So if there is this outer if is false, then you're not having any condition. Therefore in the tree, this is called a symbolic execution tree of this particular function. Okay, So when we symbolically execute this program, what is the what are the possible what is the tree of possible outcomes that we get? So we make something like a tree, and then we get the outputs out of that. So this condition can either be false or true. If it is false, then how do we reach, I mean, like, how do we make this particular condition false? What is the input so that this condition becomes false? So that is one possible input, right? There can be many inputs which satisfy this condition to be false. I mean, like, not is equal to 2 twice of 5 not is equal to x, because if you say that this is the condition, then if it is equal, then we will go to the true branch. If it is false, then we will go to the other branch, which is the false branch. So which is to say that this is not is equal to, okay, I mean, the complement basically of this particular condition. So when does that occur? That will occur when these two things are not equal, right? So how we can make such a condition? So there can be many inputs, right, which just doesn't satisfy this condition. That will suffice for the false case. So here we are giving one such possible input. Okay, so if you provide x to be 0, y to be 1, then you get 2 is equal to 0, and therefore we will get false out of this condition, and it will follow the other branch. Okay, now assuming I'm so sorry, assuming that I want to make this condition true, right? There are so I follow this branch, then I have one more constraint to solve. I'll have to have this x greater than y plus 10. So if I want to make this condition false, then this input could be taken, right? So then in this particular input node, that nice thing about this is that if you provide it to the first predicate, this input, then you're going to get a true. So you follow this branch, but for this other condition, it is going to be false. So that is nice. So I mean, like, if you want to have a situation wherein the first predicate is satisfied but not the second, then you provide this. If you want both of them to be satisfied, then you can provide this. And note that there can be other possibilities also, but these are just sample inputs that are given. Okay, now note that when you have this particular input, then you will be able to reach the error state. Okay, is that clear? So sorry.
Yes, yes.
Okay, so that is what happens. Now, a very nice thing to note about this is that when you get the input, and we'll talk about how are we getting inputs from these conditions, these path constraints that we are making, how are we getting the actual inputs like concrete inputs, how are we getting 30 and 15 and all that. We'll talk about this. But then the nice thing about this, once you have this, no, you can have your own test case, because you got the inputs, right? You know how to reach error, and you got the inputs, then you provide this back to your function, whatever function it was, test me function. If you provide this value, you're certain, you're guaranteed to follow this exact path. Okay, so you come inside, you have this as true, you have this another one as true also, and you're going to get, I mean, like, you're going to get to the error statement. So the nice thing about symbolic execution is that once you have solved those path constraints, then whatever result you get out of solving those constraints, you get it in terms of the original input variables that are there, as I mentioned previously also. Now you when you provide that again, you're going to follow the exact same path. Okay, so that is what. So I mean, in some sense, you are getting different inputs for you to be able to, follow the path whichever you want to test. So if you want to test this path, true, false, then you give this input. Okay. So these are the things. Is this clear? Are
So,
there
sir,
any questions?
yeah. So, is this tree used to build test cases?
Yes. Symbolic execution is basically used to build test cases,
Okay.
depending on the various outcomes.
So, sir, one more question. If symbolic execution assume that you are aware of error part in your code,
Not necessarily. So it depends on the coverage criteria again. What are we trying to follow, right? For example, in certain test cases, we might not be aware that there is a code. I'm sorry, there is an error inside that particular branch, but we have some criteria about which we'll talk moving forward, right? Depending on that, if we cover that criteria, then that's enough. So what happens in testing is that you don't do it. I mean, like, you don't do it in one go, right? For example, you write test case, that's okay. Now your program is changing also, no? Depending on the customer's requirement, you might also make changes to the program. So it may happen that certain portions of your code which did not have an error or fault previously may may become a fault or something like it may become erroneous basically after that change. So then you run the test case again, you'll be able to realize that there is an error. I'm reaching an error state here, right? I mean, like initially it might not be there, but due to a change that happens somewhere else in the program, you might be able to figure out that there is an error. So that's what. And the manual labor is saved here, right? Of doing this. So for example, if I were to ask you without having symbolic execution anything, right? If I were to ask you that I want this condition to be satisfied, but not this condition, and at the same time I have a third condition that I want, to be satisfied, but not the fourth condition. I mean, it becomes very difficult, right? How do you ensure that you get something, some input, you know, that satisfies this exact set of conditions, and this exact set of conditions not satisfied? Like it is very complex, right? As the number of conditions grow, and as the number of variables involved grow, it is not possible to come up with manual. I mean, like it's not possible to come up with manual test cases. Like I mean, like you cannot come up with inputs manually, basically, which will satisfy that exact same set of conditions, right? It is difficult to do it by hand, no? To try to realize this, as and when the conditions become larger and larger and complex, and at the same time you have more variables which are involved in the whole process, so it becomes
Yes,
difficult.
more variable and more nesting.
More nesting, yeah, more nesting, more conditions. So you talk about these kinds of applications. Let's say tax calculation, for example. No, this is a very that's a very I mean, a good example because I take it so many times. So what happens is that tax calculation, you have calculations only, right? And it's easy in that sense, but there are so many conditions, right? I mean, like the specification for tax calculation is very complex. It's not easy, right? There's so many conditions. So if that is the case, there are several you know conditions and categories under which people come. So if their income slab is this and that and all that, there's a whole lot of other conditions depending on the regional the regional I mean, depending on the region from where they're applying, there can be other things and stuff like that. There's so many things. I'm not aware of what all exactly is there, but you can imagine that in such a complex system, there's so many conditions that are possible, right? And to, to be able to come up with inputs that satisfy each of them individually is very difficult, right? So we need to have some kind of automation in that regard, and that's just one example that I'm giving, but this is used extensively in other places also. So so yes, to your point, basically, whatever we are doing is just to make sure that we are getting the inputs and we are getting it exactly as we want them to be. Like for example, if we want this to be true, this to be false, then we are getting that. So for each case, basically, we are getting one. That is what happens. Okay, is that clear? Shall we move forward?
Yeah, yes, sir. One more question, sir.
Yeah, yeah.
So, you told me that we are not going to manually feed the test cases because it might be
Create,
difficult to create.
create, yeah, create manually, because if you just know the conditions, right? How do you come up with test cases that exactly satisfy these many conditions and not the other ones? How do you do that? It's
So then,
difficult, right?
what is the purpose of building this tree? Will this be used in some automation?
Yeah, yeah, of course, of course. A certain, I mean, like it depends, right? I mean, we are not going to build up the entire tree possibly, because, as you know, for any predicate there are two possibilities, either true or false. So as the number of predicates grow, you have 2 power n possibilities, right? So such a tree will have basically 2 power n levels, so 2 power n branches. So of course we are not going to do that, right? For every case we are not going to do that, but certain cases if you want to test, so you take a subset of that. So for example, if I want to test only for such a scenario where this becomes true and that becomes true, then I can take this one only, right? The rest can be discarded. Does that answer your question?
Yeah, yes, sir.
Okay, okay. Thank you. As we move forward, things will be more clearer, I believe. So let's move forward. So yeah, now before moving forward with other things in symbolic execution, we just like to introduce program proving also. Just an introductory statement here. We're not going to go in detail of how program proving actually works, but what program proving says in contrast to program testing is that you must prove mathematically that whatever your program is supposed to do, it is doing that. So we are having a formal proof of that. Now think about this. In complex and large programs, the softwares that we are having these days, it is very difficult to prove formally, right, that the program that you've written is correct in that sense, right? Proving it rigorously mathematically is difficult. right? So that's why we go for test cases. We provide input and see if the expected output is matching with that actual output or not, and that's what we do generally in practice, right? So proving is difficult, but it is mentioned here just so that we understand that there is a program proving, there is a notion of program proving also, and at the same time, uh, for small sections, like subsets of the code, we can do that, right? Where it is possible to actually prove. So there we can use proving, but to do proving, to do a proof, a formal proof for the entirety of the program is difficult, right? Because the program is complex now. How do you do proving for the entire thing? So it becomes difficult. Okay. So that is what it says in programming. Basically, theoretically says that we have to prove that the programs are correct. This is different from testing. Okay, please don't confuse it with, in testing we provide the inputs and see if the expected output, it is matching with expected output or not. That's all we do. Here we are proving it. So basically we are getting up with a proof that says that whatever we have is correct only. So this is different. Now here two things are mentioned. First is that test cases are not exhaustive. This I think I mentioned previously, one of my previous classes also, that when you are testing you can't be sure formally that your program is indeed free of all errors. It is never possible, right? As one of the computer scientists said once, it is never possible to say that the program is free of all errors, but we can test the correctness on certain test cases. Like for whatever inputs you are providing, you're sure about that, right? That okay, under these kinds of inputs at least my program is going to work. But to say that software is correct in general is not possible, because you cannot test it exhaustively for all possible inputs that might come into your program, right? Especially for large programs, it's not possible. So therefore, in general, exhaustive testing is never possible, okay, in practice. So again, that is the same thing is as mentioned here. So it says that okay, we are testing for certain inputs. There are finite set of inputs, no, we have in test cases. We do that, but for the other inputs, it is not tested, right? So then again, therefore, exhaustive is not possible. Okay. Okay. Program proving involves formal methods, as in there's a technique called formal methods. I think it's is related to mathematics also. So therein we use techniques to prove as to whatever the logic is written for the code and other things, that is correct, as in whatever the requirements have been specified for that particular part of the source code at least, that conforms to that. Basically that is satisfying those requirements. Okay. So this is a different case. Okay. Now, what are formal methods? Formal methods involve mathematical techniques that are based on deriving formal models from a program. So basically, what we do is that we have a program, we try to derive some models of the program, and then we do uh, prove, use mathematical techniques to actually come up with our own proofs based on derivation. Okay, so this is how it works. So, okay, there are three techniques under formal methods: model checking, or theorem proving, or program analysis. But we are not going to go into detail of these things. Okay. Now, again, some discussion about what is difference between testing and proving a program. So, program testing and proving can be considered as extreme alternatives, of course, because on one hand, you have proving, which says that no matter what input you give, I want to prove that my program is correct. Yeah, uh, that's one possibility. The other possibility says that you just provide me a limited set of test cases. I want to test that under these test cases the program is, if it is working, then I'm happy with that, then that is testing. So that is the other thing. Now that is what it is mentioning here also, that whatever sample test you gave, that runs correctly. Okay, we check the results if it is matching, and some other necessary checks that are in place. If it is okay, we will say that's okay. I mean, like, we give it a green light basically. And if it is some of the test cases are failing, then we might go back and possibly fix certain errors that might be there in the software. So that's okay. And yeah, again, same thing. So correct execution for inputs not in the sample, right? So whatever your program has not been tested for is still not, because you can't be very sure that okay, these kinds of inputs are not tested, so I'm not sure whether my programs are working under that input or not. So that is what the difference is. Same thing is actually repeating here. So in program proving, we formally prove that it is meeting the specification. Whatever was specified, it is meeting the specification. And one more thing. So it is done without actually executing the program. So in proving, we don't actually execute the program. We just mathematically prove it theoretically that the behavior is correct. So it is therefore it is difficult also to do it in practice.
Sir, one question, sir.
Yeah, yeah, please.
Okay, can I say that in programming proving, we just logically see whether code is correctly written or not?
Yeah, yeah. To some extent, your point is valid. That we just see, but just seeing it, like just reading the code, doesn't make one sure that whatever is there is correct only, especially for complex code that is there. So to prove it is difficult. It's like mathematics only. When we say that, let's say for example, I have this series that converges to this particular value. I mean, and that's a statement, right? But to prove it is an entirely different thing. Or I say that this Dijkstra's algorithm always gives us the shortest path, right? But we have to prove it, no? Dijkstra's algorithm always gives us the shortest path, but there is a proof for that. Therefore, we are saying that, no? There is an algorithm which is guaranteed to give us the shortest path. That is Dijkstra's algorithm, but that we know. But until unless somebody proves that, and that's what Dijkstra did. So Dijkstra, when he came up with his algorithm, he also gave us the proof of why it is going to be correct only, and therefore we understand that okay, this algorithm is complete and sound as well. So there is this notion of completeness and soundness when we talk of algorithms, you know. So that is how we formally prove. So you have to theoretically say that. In uh, yes, of course. To begin with, a quick check through the code to see if the logic is correct or not, as you said, might be okay for small programs. But no, but here we are talking about complex programs, so let's say algorithms for that matter. Then one cannot be sure without proofs. Okay, so we have to anyway do it theoretically. There is no other way around. Until unless you prove that, I mean, like until unless you give that proof, it won't be considered uh, valid. So that is what. Does that answer your question?
Yeah.
Okay. So yes, again, here it is mentioned again. So not all proofs can be automated, and most proofs need to be done by hand. So you have to do it by hand. Basically, it is difficult to automate that. So to certain extent, it can be automated, like as we've seen here, model checking, theorem proving, and program analysis. For software exists for these things also, but not to the fullest extent. So we have to, after all, do it by hand at least as of now. So now we've talked enough about program testing and proving. So what symbolic execution then says is that it is a practical approach between the two extremes. Okay, so on one hand you have testing, which is just providing concrete inputs and testing on that, and proving says that we will not run at all. You just theoretically prove whether it is correct or not. So what symbolic execution says is that let's do something in between. We do some amount of testing and as well as proving, because note that in symbolic execution we are having just variables, right? So if we are getting correct output symbolically, then basically it amounts to proving, at least to some extent, right? Because we are not providing a specific input here. We are having a class of possible inputs that can be there, because everything that satisfies that particular constraint and we get into that particular branch of the code, then that is guaranteed to always follow the same path. So for example, if I come back to the execution tree, if I have this condition, then there can be many things for x and y which satisfy this condition, right? I can take multiple things. Many solutions exist to this particular predicate. Then whatever I take, right, would actually lead me to follow this path. Need not necessarily be 15 and 30. It could be anything else, right? So the idea that symbolic execution says is that we can at least partly prove that portion, like we can at least test in such a way that certain portions of the code need not be tested explicitly for all inputs that are possible. So if we test it for one such input, like in this case, if we take 30 and 15, then we are satisfying for this branch, these two branches, we are getting true and true for this particular input. And then in that case we are actually checking for all other things which would also satisfy that. Like for example, for one input, if you're following this branch, then for all other things that might actually lead us to follow this path is also covered, right? I mean, it can be anything else, but it needs to satisfy both of them. So I'm not able to come up with anything for now. I mean, We can have something else. Let's say not 30 and 15, anything else. So by checking for one of them, we have checked for all of them basically, right? Because no matter what you do, you're going to follow the same path as long as these conditions are being satisfied. Same goes for this one. Okay. So this is false and this is true. So it means that if you provide this, this covers for all such inputs wherever this condition becomes true and this becomes false. You need not provide anything else. That's all, right? So this is what happens when you do symbolically. You are covering for a large number of possible test cases that can be there. You need not do it explicitly. Or no, again, the nice thing about this is that when you give this, right, you follow this branch, and you I mean, like, if you just have this particular input, then you don't know what change you will make to your input so that the other branch is followed. Of course, it might be possible. Again, going back and seeing the code and trying to come up with such inputs by hand, as I mentioned earlier, but it is difficult nonetheless, right? You have to make a change such that. So here we are not doing that. Here we are generating it directly. So when we reach this part, we generate this input. So we say that okay, to reach this part, to follow this particular path, you have to have this input. Okay, so that is what happens. Sorry. Okay. So yeah, that is what it says in the third point. Each symbolic execution is equivalent to a large number of normal test cases. And the reasoning of which I just mentioned, I'm not sure if that is clear, but that is what happens. So if for one possible input you check that you're going to follow that path, then you it is sufficient for that particular path, right? Because everything that is going to be satisfying that those many constraints are going to follow the exact same path. Right. So if you test for one of them, you you cover for basically a large other such inputs, large number of such inputs. So that is
So one question.
Mhm.
Before symbolic execution, can I
Mhm.
say that we were testing, we were building test cases
Mhm.
blindly. Now
Right.
we are building test cases consciously.
Yeah. Yeah. Valid point. So it is like an informed way of doing it, right?
Yeah.
Yeah. Your point is totally valid. So your whatever you said is correct. I agree with that. So in normal test cases, we are just trying to. I mean, like, we will not say blindly as such, because as a developer, as a tester, we are having some knowledge about the code, and then only we are providing the input. It is not that we are just providing any random input. That is not that what we do. But I get your point. Whatever you're saying is correct only. So there we are ourselves making it, but here we are taking help from the computer also to do some work for us, right?
Yes.
So so that is what. And therefore, I mean, this point is very important. So if you test for one such case which satisfies a particular branch, then whatever else satisfies this particular branch need not be tested. If you test for 30, 15, and that suffices for everything else that comes under this, that satisfies both of them. Then you go for checking other things, other cases. So that's nice. I mean, perhaps if you do, I mean, like, if you do 29, 15, 14 also, that also comes here. So there's no point in doing that, right? You check for 30, 15, then 29 and 14, you need not check for that. You just go to this one. And you get the point, right? Because it is going to follow the same path. So why do I need to test that again? Right? That is why. So that is what it says. Okay, move forward. Okay, some description about what symbolic executions are. Actually, what, so I think most of it I've already discussed in this class itself. So we'll just go over that quickly. So symbolic executions uses symbolic values as we discussed. Okay, instead of concrete values as we discussed. Okay, so instead of providing concrete values, as in the actual values or the numbers, we're having symbolic values. That is x naught, y naught, or whatever symbolic names you want to provide to that. Okay, program variables are represented as symbolic expressions that we have seen here also. Coming back just to relate. So for example, x is alpha 1 plus alpha 2 instead of saying some concrete value. Okay, because we have variables to start with, we are just building in terms of that. These are the expressions that we are getting. Okay. Okay. Mm, yeah. So hence the output values computed by a program are expressed as a function of symbolic input values. That is what I was saying initially also. Whatever you are getting, you are expressing it in terms of the original input variables that you have for the function. Okay. So when you provide that back to the function, you are guaranteed to follow the exact same path. Okay. So this is like a function, right? You're providing something, the program is run as a function, then whatever you get is expressed in terms of the actual inputs that you had. Now you solve that constraint, you get actual values now, you provide that back again to the program and you're going to follow the exact same path. And that is what you see moving forward. So this is the symbolic state. It is denoted by a sigma that is mapping the variables to their symbolic expressions as we have seen earlier also. So for example, here z is equal to twice of y naught. Okay. So this is mapping z to its symbolic value, whatever it holds at that point in the program. Okay. Okay, coming back, we have the symbolic path constraint, which is a predicate, basically quantifier free first order formula, which is to say predicate, you know, over symbolic expressions, as we've seen in this case. So here, this is a predicate. This is a path constraint. Okay. Again, so this is more or less discussing the same thing that I mentioned earlier. So it says that symbolic execution is to generate a test input for each execution path of a program. Notice this. Okay. So we can generate, I mean, how many ever we take, it's a different thing, and there are several stopping criteria also, as because I mentioned that uh, the the space of or the set of possible test inputs that can be there, if you try to see every condition in isolation, you make it true once, you make it false at another time, then it becomes 2 power n, which is too much, right? If you have a lot of conditions in your program, then it sorry, then it becomes difficult to test for all of them, and therefore we'll just take a subset of whatever comes out, but that's okay. An execution path now that I've been mentioning is a sequence of true false, right? So for the first condition you have true, for the other one you have false, right? So there's just a sequence of true and falses for the conditions you have in between. So for example, if I were to go back, this is the first condition, right? So it's true. The second condition is true. This is the sequence, right? True false, or so we can have true true, true false, or just false, something like that. It's just a sequence of true and false depending on the path. So this is the path, right? The edges are the paths basically. So we come in, yeah, this edge, that edge. So to follow this path, this true false, so it needs to be true false. So this is the sequence basically. When we say sequence, that is the sequence. Okay, all the execution path of a program can be represented using a tree called the execution tree, and that is what we have seen above. Okay, so we'll talk about symbolic state now. Is this clear, the execution tree and this part?
Yeah, yes, that's good.
Okay, okay. Now at the beginning of the symbolic execution, sigma, that is the symbolic state now, is an empty map or dictionary, whatever you want to call it. Basically it just maps. Now every time a statement is read, that is what I was mentioning earlier, symbolic execution adds the mapping, assigning the variable to being read to its new symbolic variable into that map. Okay, so when we come here, this part, we were here line number 4, nothing is there, z is not there. We come to line number 5, then z is being added to the symbolic state, and its value will be twice of y naught, whatever value we get, and then z gets added to the symbolic state. So as and when we move forward, so assuming that there is a c is equal to 10, let's say somewhere here, no, line between line number 9 and 10 here. Okay, then in that case, when you reach this particular place, you will have c is equal to whatever, then the state gets updated. Okay, so that is what happens. Coming back, I'm sorry for scrolling too much, but I was just trying to relate it with the example that is given. Okay, so that is what happens. At every assignment, symbolic execution updates sigma, that is the symbolic state, by mapping the variable to the computed value of whatever. Let's say, for example, in the case of a, we have alpha 1 plus alpha 2. So that is the new value for it. When we initialize, it is something. When it moves forward, it is getting updated, and it is getting a new symbolic expression as long as the program runs. Okay, it might not all, I mean, like, it might not change also. It is not necessary that it changes for every variable. Whatever variable is changing, you'll change that in the symbolic state also. Okay. So sorry. So yeah, initially PC, that is path constraint initialized to true, because you have to follow. I mean, like, you have to start, right. If you just say false, then you're not going to move forward. So you have to have the very first thing has to be true, and therefore, in the table that we've seen earlier, the very first path constraint was true initially here. After statement one, the very first path constraint is going to be true only because you have to start, no. So the first one is going to be true. So that is what happens. Right. And the same thing. So what happens if a conditional statement occurs, some expression is there, then so we we have the if condition, something like this. So if E is true, then we follow S1, else we go to S2. That's okay. Now we'll add this this two. If we have a if we have to follow a then branch, right? I mean, if we have to go inside, then we will say whatever the condition is, E is the expression, that is the condition is which is under the if statement. So if we want that to be true, then we and it again, right. Map from the symbolic state, whatever that expression is holding, we just and it with the current path constraint, and then it goes to the then branch. if if we have to have a condition wherein it doesn't follow, like we don't want to go inside, the other case or the complement of that, we say PC prime. PC prime is the other constraint, the complement of that, and that is going to be not of whatever we had. So earlier we had this condition. When we want to complement it, we say the else part, which is to say it is not of whatever it was. So if it was false earlier, then the true case will be the other case. If it was true earlier, then the false case will be the other case. Whatever the case may be, we just invert that condition basically. So that becomes the complement. Okay. Okay. So that goes to the else branch. So we generate both of these, at every stage, as we've seen in the symbolic execution tree also. Okay, now the path constraint or the path constraint prime, which is the complement, if any of them is satisfiable for some assignment of concrete symbolic values, okay, concrete two symbolic values, okay, whatever path constraint we get, we solve it. How do we solve it? We'll come to that. We solve it, and then we will get a concrete value out of that, as we have seen in the case of the symbolic execution tree also. At the end, we got this, 30, 30, 15, and so on. So that is what we do. Coming back, we have, yeah, this we have seen, I guess. Okay, no, this is the same example. We're just running on that. Okay. Yeah, this part is clear, I guess. So if it's satisfiable, then we'll get that. We'll continue it. Otherwise, if it is not satisfiable, as in there is some condition which cannot ever be satisfied, right? Let's say if you say something contradictory, contradicting condition. Let's say if you say that A should be equal to B, so you say A is equal to B, and you're doing an and, right? So you do A. I'm just making an example condition which is contradictory. Okay, so you say A is equal to B and A should not be equal to B. So that cannot be true at all, right? It's a contradiction, right? We cannot have both conditions becoming true at the same time. That A is equal to B and at the same time it is not equal to B. So that's a contradiction. So that is what. So when you say it is satisfiable, which means it can be satisfied, no? For some input, for some variable it is there, that is it is satisfiable. Then we will continue. If it reaches some kind of a contradiction or a condition which is not satisfiable, then we go to the else part. So it depends on whatever the condition is. We'll come to that. How do we solve it? Now, yeah, unlike concrete execution, yeah, note that one more point is there. In concrete execution, we'll follow one branch only, no? Let's say if you have 1530, then you are going to go into the true case only. You'll never go to the false case because for one concrete input, you're going to follow only one branch. There is only one execution path corresponding to that particular input. They're going to follow one branch only. If so, in this case, however, you can follow both simultaneously. So the symbolic execution continues on both branches. So you go in one case, you go inside, in the other case, you don't go inside, and both of the execution flow is still continuing. Right? So you don't stop there. You continue as long as the program is there. Okay. Now, if any of the path constraint or path constraint, I'm calling it prime. You can call it something else. It is just a complement. So the true case, the false case, basically. So if any of these is not satisfiable, then for that path you stop. Okay. for that particular path. So if you come back to the execution tree, if you reach here, let's say if this is false, for example, and there's nothing, but there can also be a condition which is not satisfiable or anything like that could happen. In that case, you will stop further expanding on this branch. You'll not expand this branch because there is nothing after that. However, um, as long as you are getting conditions which are satisfiable, you will continue. Okay, so you'll keep going in that direction. And there is this termination criteria by which we stop. So how do we know when to stop and all that? So that is there. Okay. Uh, where were we? Yeah, here. So yeah, same thing. So next slide. At the end of the symbolic execution, yeah, the path constraint is solved using a constraint solver. So we got the conditions, right? We got the constraint. Now what do we do with them? As a result of symbolic execution, we got the constraints. Now what do we do with them? So we'll actually use a solver, constraint solver, as that is to actually get concrete inputs out of that. So basically what a constraint solver does is that it's a software only. What is the it does is that whatever condition you provide, constraint condition, it's like a constraint, yeah, exactly, constraint solver only. What it does is that it allows you to get some value, right, which satisfies whatever constraint you are providing to that. So it's general thing, right? It does that. Whatever constraint you have, it solves that. uh, it solves that predicate and gives you the value as output, a concrete value, note that, such that those conditions are satisfied. So that is what the job of a constraint solver is. Okay, so the path constraint or condition that we get at the end of symbolic execution, that is then passed to a constraint solver to actually get the concrete input values back. And that is how we get 15, 30, or 2, 1, or anything like that. Now, there can be many solutions. It just gives you one of them so that you can, run your program through that. Is that clear? The job of a constraint solver?
So constraint solver is generating test cases, right?
Right. The final input. So, okay, one more nuance that I would like to just point out. So there is a difference actually in test cases and inputs. So of course, test cases are inputs, but when we say test cases formally, it also includes the expected outputs. So when you say constraint solver is generating test cases, that not that that will not be exactly correct, because it won't know what is the expected output. No, what is expected, it won't know that. So it just generates the input, to follow that path, and that is all. What is the expected output under those conditions is your job to specify, and then you get a test case. So test case is input plus expected output, whereas constant solver is just giving you the inputs to satisfy that path, to uh, kind of make the program follow that particular execution path, whichever you want to follow. Okay, so that is what. And finally, you're going to get uh, concrete input values, as you said. So that's correct. Only thing is that you should say input values. Okay. Now, there's one more thing. So it can be terminated if the so sorry. It can be terminated if the program is, you know, reaching an exit statement or an error. So let's say an exception occurred in your program. In that case, symbolic execution won't continue for further, because I mean, like, that is the job of it, right? So if it encounters an error, let's say, then of course you reach the error and therefore it stops there, need not continue further, right? Yeah, that is what I was mentioning earlier also. If the program is executed on these concrete input values that we get out of the constraint solver, it will take exactly the same path as the symbolic execution and terminate in the same way. Right. So the path conditions, if you solve them, then the concrete values that you get, if you pass that into your program, then the path that the program is going to take is going to be the exactly the same path. Okay. This I mentioned already, but that is one more very important point. Okay. So in some sense, you're getting inputs automatically. I mean, like, generating inputs such that you are you can follow whatever path you want to follow in the execution of the program, depending on whatever input you give. But that input you are getting as a result of symbolic execution. Okay. Okay. Yeah. So this is that. The final thing, like, why are we doing this? So These concrete inputs ensure that coverage is achieved in testing by taking different execution paths in the program. So let's say my coverage criteria says that I want to take all. Of course, it is not possible to cover for all execution paths, as I mentioned, because the possibilities are exponential, 2 power n possibilities. So that is not possible. But whatever coverage criteria you have, let's say for some of it, I say that okay, these 4 conditions, please check for, please check for coverage for these 4 conditions. These all 4 such scenarios should be covered. Then in that case, you use this symbolic execution to get the concrete inputs so that the coverage is achieved. Okay, by taking the different execution paths that are possible in the program. Is that clear at this point?
Yes, sir.
Okay, thank you. So we are coming back to the same example. Just give me one moment. So we are just running through it, no, how it would work theoretically. I'll just go through it quickly. So, after line 12 and 13, this is the state map. So X is holding X naught, Y is holding Y naught. So this is that, no, the very first one. Because note that main is the first thing you get into, right? So that is why we are starting from line 12 and 13. So we have the state map. State map will have X map to X naught because as of now we don't have anything. We just have the variable, like the symbolic value for that. And y is y naught, where x naught and y naught are the two initially unconstrained because there is no constraint. No, we're just starting here. This is the state map node that it gets updated every time you encounter any variable. So let's say at line number 5, as I was mentioning earlier, you get this z is equal to twice of y naught. So z gets added. No, you were asking in the table when we've shown the table, right? In the table we have everything, but here actually in the state map, as and when the variable comes in the code in the execution path, that will get added to the map, the symbolic state map. Okay, so yeah, that's correct. So when we follow the execution path, we will keep adding that. But since we were making the table, we added everything because we knew what is the code and what are the variables that are involved. But in symbolic execution, systematically, this is how it is going to happen. Okay. Now, line number 6 is the very first condition that we encounter. Okay. So here we generate two path constraints. One where that is followed, the other where that is not followed. So basically, whatever the first condition is, you just take a negation of that, okay, not of that. So if you have x naught is equal to twice of y naught, then the not of that would be x naught not is equal to twice of y naught. So that is what. So each condition, for each condition, you have two possibilities, and you generate two constraints. No, therefore, that is that is what PC and PC prime are about. Okay. Okay. So line number 7, what happens? You have this. Okay. Yeah. For line number 7 also, one condition is that when you wish to go inside, you have x naught greater than y naught plus 10, which is the condition, and the negation of that would be not going inside this. So it would be x naught less than equal to y naught plus 10. That is the negation of it. Note that in both of these cases, x naught is equal to y naught must be there because this is the precondition, some sort, like the prerequisite. Because if this is not true, then you're not going to go inside at all, right? So this needs to be true. Then only you consider this. Therefore, there are only three path constraints. There are three constraints, right? In one case, oh, you have this as equal. So this as equal, this is greater than, less than, right? And in the other case, you have this as not is equal to x. So there are three cases. Okay. So solving these three cases, we get three instances of symbolic expression resulting in these many concrete test inputs, which is x is equal to 0, y is equal to 1, one case, x is equal to 2, y is equal to 1, the other case, and x is equal to 30, y is equal to 15, the third case. So there are three. So all these three path constraints that we you know we collected, we solved each of them and got the resulting test input. So it depends how many ever you want to solve. You need not solve every one of them, right? You can just solve a few of them, and whatever is needed you can solve that. But that is how it works formally. Is this part clear, how this algorithm is working, the symbolic execution is working?
Yeah, this is a practical aspect, right?
Right. Okay, thank you so much. Now we are coming to loops. So we have not talked about loop, right? How do loops work? So conditions are okay, but what about loops? How do we represent them? So here is one example. We have test me, which is going to run infinitely depending on the symbolic input. So if we keep on giving, right, let's say we're taking inputs from the console, let's say, I mean, like, practically, then we can keep on going values that are greater than 0 always, and it can go on infinitely, right? It will never become, so how do we do that then? So we have a program here which is taking the sum of it. So while n is, as long as n is a positive integer, we are just summing it, putting it into sum, and then we are getting a new input. So whatever value comes in, we add that to sum, get a new input. Now next input, we add that to sum, get a new input. Similarly, we keep on going like this because this is a loop. Okay. When n becomes less than 0, I mean, like, the negation of this condition is x. Sorry, not x. This is n. N less than is equal to 0, which is the negation. Then when it becomes negative, basically, or 0 for that matter, then we stop and then the program ends. This function ends. Sorry about this. Okay. Really sorry to come back. Yeah, then this function ends once the loop is over. So as an infinite number of execution paths, right? How do you know when to stop? Because you can just keep on going forever. How do we write that in predicates? How do we make predicates out of this? Okay. So the convention is each execution path is either a sequence of arbitrary number of truths followed by a false, or a sequence of infinite number of truths. Okay, yeah, that is what. So you can keep giving integers which are larger than n, it can go on forever. So we have to stop somewhere. So what happens for path conditions for loops in general? Whatever you have as the condition in which you go inside the loop, you will have that many times. So let's say you want to go inside the loop 3 times, let's say, or 4 times for that matter, or 5 times. Then you will have this ni greater than 0. Ni greater than 0 is the condition to go inside the while loop, right? It will be there 3 times. So we and that. So ni is the ith instance of n, because n is changing, not that. No, every time we provide a new input, n is changing. Okay. So we just say that the first n value should be greater than 0, the second n value should be greater than 0, and the third n value should be greater than 0. And we add all of them, all of the 3 conditions, we add it. So it's like summation, no? We do summation from I to n. I is equal to 1 to n, right? So this is like the summation symbol, it's just a compact way of writing it. So basically that many ands we have in between, right? Ni greater than 0 and the next. So n1 greater than 0 and n2 greater than 0 and n3 greater than 0 and n3 and 4 greater than 0, so on and so forth. How many ever times you want to go inside the loop, and when you want to come out of the loop, you have to, after all, exit the loop also, otherwise you can just keep on going forever. So then finally, sorry, we follow it with a false condition also, that is the negation of this. So the condition by which you were going inside the loop, you take the negation of it, and that becomes the false, the condition for exiting the loop. So you finally end it with the last condition also, so that you ensure that you exit the loop also, otherwise it will keep keep going, forever. So the last condition, you mentioned that this should be true also. Okay. Is that part clear? So whatever n you want to, how many ever times you want to go inside the loop, you just specify that in n, and that many times you will have that condition satisfied, and then finally you end up with the negation of that, so that you exit it. Is this part clear? For any loop, this is the general idea. How do we do this? In,
So, sir, this is very rare to have a infinite loop, no?
no, in this case only you have an infinite loop, right? Not necessarily. I mean, it's not necessarily like, let's say, no human is there, right? So it is running via a program. So note that the symbolic execution is also a program. Now if symbolic input function, whatever symbolic input function that is taking values for n, if it keeps on taking values which are always greater than 0, then it is going to go on forever. It will never stop, right? Does that make sense? Because the sum is going to, sum is going to get larger and larger, and you're going to go like inside always. So you have to ensure that you kind of instruct the symbolic execution algorithm also to ensure that there is a final condition also in the constraint, such that we exit also, otherwise we'll not exit. Right. So how do we express that in terms of the predicate? Because after all, we need predicates to give to the constraint solver, right? So then this is the format in which we write those predicates. The only thing is that to note is that we just mention the false condition also always. How many ever times you want to go inside? So you want to go inside 3 times, any loop. Okay, this loop I want to go inside 3 times. So I have this kind of condition, and this and this and this, and finally the exit condition, which is the negation of that. Okay, so that you exit. So yeah, I mean, it can happen that there are infinite loops. So if you have a loop such that it goes on infinitely, then the way to express that is to this is the way to express that, basically the standard way to mention that. Okay, now notice what happens to the state map when the loop is exited. Okay, so oh, I'm really sorry about this. Okay, there should be a back button. So we come back. Yeah, finally what happens when you exit for this particular example, n is holding the value of n of n plus 1. So how many ever times you wanted to go inside, let's say n cruise, right? That is what it says, n number of times you go inside the loop. So let's say I want to go inside 3 times, and the fourth time you want to go inside, this should be false. So n's value would be I mean, like, four different n's would be there, right? 3 times it will satisfy the condition. Let's say 1 2 3, whatever value it is, right? And the fourth time we take a negative value. So in this case, let's say I want to go inside 3 times this loop, then I can have n as 1 for the first case, so it will satisfy, n as 2, n as 3, and then finally I'll give n as 0. So this will become false and we'll exit. Okay, so 1 2 3 0. So the value for n at the end of the execution would be 0, right? Because the fourth value, the last value by which we exited this loop would be there in the state map in this particular case. And some some would be just the summation, because that is what we do, right? We just take the inputs and sum it, right? So the sum at the end of the execution, at the end of the loop, would hold the sum of all the numbers that are present there. So we have summation I to n ni. Okay, ni is a different value each time. Each time you go inside, you get a new ni, right? Because you're taking the input every time. Every time a new input is taken. Okay, is this part clear?
Yes, sure.
Okay, thank you so much. Now, this is general programming, right? So in general, symbolic execution of code containing loops or recursion may result, that is what your question was, I think, may result in infinite number of paths. You can keep on going forever, and the path gets longer and longer and longer, right? This execution tree, it becomes infinite in that case. So if the termination condition is not specified, so yeah, if the termination condition for the loop or recursion is symbolic, yeah. So therefore, we have to have, one needs to put a limit. How many ever times you want to go inside a loop, right? A time or a limit on the number of path or loop iterations or exploration depth. We call it depth also. Like going deep inside the tree, the depth is increasing of the tree. So we have to have a limit, and therefore we have this n in place, the small n. The small n says that this many times I want to go inside, and then finally I'll exit from there. And this convention is followed for the while loop as well as for the for loop. Okay, whatever loop it is, this is the way to express that. Okay. Okay, sorry. Several other programming constraints need to be handled to develop yeah, of course there are other things also, no, do while loop, and what else is there, branching is there, switch case is one thing which is there, right? Other kinds of control flow structures like constructs are there. So for all these, there's a way to express them in a predicate fashion. Okay, all right. So we'll talk about satisfiability briefly, and then I think we can close. So symbolic testing is dependent on a constraint solver, as we've discussed so much about this now, and that takes a path constraints and gives a set of input values to be used as test case, basically generating the input values that will be there for the test cases. Okay, and the test cases, not that will have expected outputs also, but it is not giving you that. Expected output you have to provide it, but inputs it will give you. Okay, now these inputs values are solutions to the path constraint, and these are no, this problem, problem of having a constraint of a predicate and solving it such that it becomes true is known as the satisfiability problem. Because what all I'm asking for is the set of values such that my predicate becomes true, and that is what the problem is. So this is not known as the satisfiability problem. What inputs would cause this particular predicate to become true? Okay, now satisfiability problem, it so happens, computer science, for constraints, you know So there is two ways of writing this. There is this first order logic also, and propositional logic like Boolean, Boolean algebra and all. So for propositional logic, you have this satisfiability problem is NP complete, which is to say that it requires exponential search space. Basically, you have exponential time complexity for those who are familiar with the algorithms. You know, you might remember it from the algorithms class that we have a notion of polynomial time and non-deterministic polynomial time algorithm. So there are two classes of course there are other classes also, but there's this NP and P problem, P versus NP. So problems which come under non-deterministic polynomial time are considered to be hard problems. We also call it NP hard problems, right? Because the time complexity is exponential there. Why it is so that for satisfiability problem it is exponential? Because it's the same reason. So let's say you have n clauses, right? N clauses in a particular predicate you have. Then then if you want to test all such possibilities, then you have 2 power n possibilities because each clause can become true once and false once. So there are 2 power n possibilities, similar to what happens in combinatorial coverage criteria also that we have studied in the previous weeks. Okay, so we have 2 power n possibilities and therefore it is hard, the exponential, and it is not easy to actually you know do that because the search space is exponential. Okay, when the format of writing that constraint is in first order logic, this is a different thing. This is a different way of writing logical expressions, logical statements. Then the problem becomes undecidable. So no computer can actually decide whether it is solvable or not. But in general, what happens in symbolic execution is that whatever constraint we are going to get is going to be in propositional logic only. This one, the first way of writing it, propositional logic. So this is fine. I mean, like we'll get it in propositional logic that is solvable. That might be solvable, but then it is NP complete, which is to say that it is hard to do that efficiently, and that is what it is mentioned. So if the path constraint that is generated during a symbolic execution contains formula that cannot be efficiently solved, at least it's a tough kind of formula which for which you have to look through the entire possibilities, then it becomes difficult, right? Then this is one of the disadvantages. Okay, then if you have such a formula, of course in practice it will not have happened that many times. But if such such a thing occurs, then it cannot generate test inputs. So that is what the disadvantage of symbolic execution is. So if the constraint that is generated is not solvable efficiently by any of the constraint solvers that we have, then of course we cannot get test inputs, and this is a disadvantage. Is that part clear?
Yes, sir. Yes, sir.
Okay, thank you so much. Yeah. Now finally, again, same thing. So just repeating the same thing. So PC generated during the symbolic execution cannot be solved. This is disadvantage. It is possible that in certain cases the path constraint that is generated it cannot be solved in two ways. So I mean when we say it cannot be solved, as in if it is contradictory, the example that I gave earlier, a is equal to b and a not is equal to b, so that is solvable as in we can say that it is not, like it is contradictory, so it is not satisfiable, there is no such possibility. I mean, like we are able to get to a conclusion, right, that okay, this is a contradiction and you cannot satisfy it. That is a different thing. When we say cannot be solved by any constant solver, which is, it is not to say that that's a contradiction or anything like that. It is to say that efficiently to come up with a solution for that is difficult even for a computer, because there are 2 power n possibilities, and to get to generate test inputs therefore is not possible, right? But in practice, as we'll read for going forward, these days the constraint solvers that we have can handle hundreds of thousands of variables, and they can efficiently give us the inputs for that, right? So it's okay, but theoretically we should be aware that it is an NP complete problem, and therefore in general uh, it is difficult to come up with uh, inputs, but it's okay. I mean, like in practice these kinds of constraints are rare, so most of the time we get something which we can keep and move forward with that. Okay, one more disadvantage: if you have a program which uses functions for which the code is not with you, for which the code is not available or which is not with you, let's say in websites and server and client applications, we have a client sending a request to a server, and the server is actually doing something on its end and giving you the output. In that case, the code is not with you. Then how do you do symbolic execution? Because you're not aware of what the server is exactly doing, right? So then that's another disadvantage. So to some extent, we are able to mitigate that this particular problem with something known as concolic testing. Okay, which maybe we'll discuss in the next class, not today. Right. So this particular thing, but symbolic execution in itself, this is a very important thing to note, that this is a disadvantage, that if the code, of course, is not available, how do you do symbolic execution on that? So of course, this is something that we will discuss in the next class.
Hello.
Yeah, thanks for the heads up. Am I still audible?
Yes, sir, you are audible.
Okay, okay. I hope I was able to convey what I was trying to say just before this. Is that part clear? This one, this point?
Yes, sir. This is clear that if
Hmm.
a tester want to test or do some symbolic execution, they should be aware of the actual code.
Yeah, the entire code, right? Otherwise, like in I was giving the example of a server client application, right? So if you have a server, if you have a client application which is sending a request to a server, and that server is doing the actual computation, then you don't know what the server is doing, right? You're just getting the output. In that case, to come up with path constraint is not possible, right? That is the disadvantage. Okay, should be aware of that. All right, we'll move forward. Just give me one moment. Just go with this. One moment, please. Just coming.
Yeah, I hope I'm still audible.
Yes, sir, you are audible.
Okay, thank you so much. Yeah, so yeah, many real life programs have huge number of program paths, resulting in several path constraints, as we discussed earlier. Exploring all paths, again for the same reason, that the number of possibilities are exponential and there are 2 power n cases, uh, it it might not be possible or infeasible, right? Of course, it is not possible because uh, there's so many constraints that are there that you can do. But again, for modern day symbolic execution, the solvers basically, as I was saying, that the solvers can actually do uh, handle thousands of variables and the things that are there. So the path conditions that are there, to solve them is not so difficult. So you can actually solve them these days. Very good SMT solvers are there because the computers also becoming better, no, at processing data, and have more memory also. Therefore, these SMT solvers are able to do that. It's okay, but still theoretically we should be aware that in general that the satisfiability problem is going to be NP complete only, but it's okay. Okay, now again, so the second disadvantage which we were discussing, the underlying program whose functions is not available or is not with you. This particular disadvantage can be mitigated using another technique which is known as concolic testing. This we'll discuss in the next class, as I said. Okay, not today. So we'll see uh, how to do it in a fashion that when the code is not available, basically we'll provide concrete inputs there, and when the code is available, we'll do symbolic execution. So that is what concolic testing tries to do. Okay, we'll discuss this in detail maybe in the next class. That is all for today, I believe. So there is this algorithm called DART, directed automated random testing, which is used for concolic testing, and this we'll discuss going forward. Okay. It works similar to how symbolic execution works, but there are several other things also which we need to be aware of. That is all. Some some tools for so sorry for this constraint solving are mentioned here for different programming languages that are there. Okay, the JQt is for Java, and This thing called PEX also for .NET and other languages.
Okay, sir. You may discuss in the next session.
Yeah, yeah. The on-calling testing we will discuss in the next live session. And if you have any other questions relating to the topics discussed till now, including on-calling testing and the previous weeks also, please feel free to ask on Discourse. We'll be responding on that before the exam as well. Yeah.
Sir,
Thank
one
you.
question here. For which disadvantage concurrent testing is used? You have told me.
Yeah, this one. The second disadvantage which was there. Yeah, here. If the code is not with you, what do you do?
So in concurrent testing, we still use symbolic execution.
Yeah, we use. So sorry, we use it, but wherever you don't have the code, you provide concrete inputs. You just give actual values there. Wherever you don't have the code, because you don't have the code, so you cannot generate the path condition, right? So there you give normal input, like you randomly generate input and give that. But if you have the code, then you generate the path constraint and solve it, similar to what we do in symbolic execution also, right? The second disadvantage. So this can be mitigated, mitigated actually. Sorry,
Okay, sir. Thank you.
this one. Yeah, yeah. All right. Thank you so much. Are there other questions that you would like to ask, or shall we close?
Yes, sir. You will close, sir.
Okay. Okay.
If I have question, I will ask on
Yeah,
Discord.
yeah, sure. Thank you. Thank you so much for joining and being with us for so long now. I understand that. But it was pending for like the previous two sessions. So I thought just I'll just cover it so that it is there in the recording so that people can get benefited from this also later on. All right.
Sir, even
Thank you.
I was attending this live session for the first time. I was just going on YouTube for to watch the
Okay.
recording.
Okay. Okay. I hope the recordings were helpful to you previously.
Yeah. Recording is
Okay.
helpful.
Okay. Yeah. Thank you. Thank you so much for attending also, Manish.
Thank you, sir.
Good night. Good night. Yeah.
Good night.